Welcome to part 4 of our series. Get started with ML agents in Unity. In this episode, we'll continue developing the Turtle agent, complete the setup of our Unity scene, and then run our first training session. In the last episode, we set up our Unity project, created the environment, and wrote most of our TurtleAgent script. If you haven't completed parts 1 through 3 yet, make sure to do so first. This tutorial picks up right where the last episode left off. You can find the tutorial series playlist linked below. So without further ado, let's jump back into the TurtleAgent script that we were working on at the end of part 3. If you remember, the last thing we did was implement the code that runs when the agent successfully reaches its goal. Now the next thing we will do is penalize the agent when it bumps into a wall. I also want to visually indicate this by changing the turtle's color to red whenever it's in contact with a wall. Add this onCollisionEnter method to your script. OnCollisionEnter is a built-in Unity method that gets triggered the moment our agent collides with another object. In this case, we check if the object has the wall tag. If it does, we apply a small negative reward to discourage collisions. Additionally, we change the agent's color to red as a visual cue that it has hit a wall. Next, add this onCollisionStay method. This method runs continuously while the agent remains in contact with the wall. Again, we apply a small penalty for this. Finally, let's add onCollisionExit. OnCollisionExit will run when the agent moves away from the wall. Here we reset its color back to blue, its default color. Alright, we have the main functionality of our script in place. Let's head back to the Unity editor and finish setting up our environment. Now let's take that TurtleAgent script and attach it to our turtle. Go to the hierarchy view and inside the environment object, select the turtle game object. In the project panel, you should see the TurtleAgent script. Drag it onto the inspector to add it as one of the turtle's components. I'm placing the TurtleAgent script just above the material component. Notice that a Behaviour Parameters component has also been automatically added along with TurtleAgent. We'll come back to this shortly. First, we need to link the goal object to our TurtleAgent script. Go back to the scene hierarchy, then drag the goal game object onto the inspector. Drop it into the goal field in the TurtleAgent script. The script is now able to reference and control the goal game object. Now let's turn our attention to the Behaviour Parameters component, which attached itself when we added the TurtleAgent script. Indeed, an agent script is always paired with a Behaviour Parameters component. But why is this important? What is the purpose of this component? Let's start with the basics. To recap, an agent is a game object that interacts with the environment, collects observations, takes actions, and receives rewards based on its performance. In our case, the turtle is the agent. It observes its surroundings, decides where to move, and learns through trial and error. But an agent alone isn't enough. It must be linked to a behavior, which serves as an interface between Unity and ML agents. In ML agents, a behavior is an object managed by the Python backend. The official documentation states, "A behavior can be thought of as a function that receives observations and rewards from the agent and returns actions. The process that determines these actions is called the policy, which is typically a neural net. But we'll cover that later. You may have noticed in the diagram that there are a couple of agents linked to the same behavior. This is because multiple agents can share a single behavior, meaning they will follow the same decision-making logic. Now, let's return to the Behaviour Parameters component and see how it connects everything together. Essentially, the Behaviour Parameters component acts as a bridge between the agent and its behavior. It tells ML agents the range of observations the agent will provide, as well as the types of actions it can take. The first thing we should define in Behaviour Parameters is the behavior name. Since our turtle agent needs to be assigned a behavior, let's set the behavior name to turtle. This tells ML agents that our turtle agent belongs to a behavior called turtle. In our case, this behavior does not exist yet, so ML agents will create it automatically when training begins. The next thing we need to set is the vector observation space size. As previously discussed, in a reinforcement learning context, a vector is basically an array. Here, we need to define the size of this array in terms of floats. If we refer back to our TurtleAgent script, you will see that in Collect Observations, we add 5 float values as our observations. Therefore, we must also set space size to 5. Next, we have the Stacked Vectors field. By setting stacked vectors to a value greater than 1, we can stack multiple frames of observations together. This buffer of previous observations is then passed to the behavior along with the most recent observations. This allows the decision-making process, or policy, to take past information into account, creating a kind of memory. So, for example, by receiving a series of positions, the policy can infer velocity. In our case, however, we will leave this setting at its default of 1, since we only want to use the latest observations. Okay, let's move on to the Actions section. We have previously discussed the difference between continuous and discrete actions. As you know, our agent is limited to a small set of discrete actions in this project. However, you may be wondering what is meant by discrete branches. Let me explain. Discrete branches allow the agent's policy to select multiple independent actions at the same time. Each branch represents a separate decision category with its own set of possible actions. So, for example, let's say we're building a car driving AI for a racing game. The car needs to make multiple independent decisions at each step, such as steering, acceleration, and gear shifting. To achieve this, we could set up 3 discrete branches. The first branch, steering, would control the direction of the car. Here we could have 3 possible actions: turn left, go straight, or turn right. Next, we have the acceleration branch. This would allow the car to adjust its speed with actions for braking, maintaining speed, or accelerating. Finally, we have the gear shift branch. This would let the car change gears with actions for shifting up, shifting down, or maintaining the current gear. Since these are independent decisions, using discrete branches allows the policy to control all 3 aspects of driving simultaneously, rather than forcing it to choose just one action at a time. Anyway, in our project, to keep things simple, we won't be using multiple branches. So for now, leave discrete branches set to 1. We may, however, change this later on. We do need to change the branch 0 size, though. As our turtle can perform a total of 4 actions, set its value to 4. We won't worry about the remaining settings in Behaviour Parameters right now. We'll come back to them in a later video. For now, there's one more component we need to add to our turtle to make our agent trainable. Scroll down to the bottom of the inspector and click the Add Component button. Then, search for and add a Decision Requester component. So what does this Decision Requester do? Well, an agent needs to decide how often it should request a new action from the policy. We could manually control when the agent requests a decision using the TurtleAgent script. But for this project, I've decided to use the Decision Requester component instead. The Decision Requester will make the agent automatically request new decisions at regular intervals. If you take a look at the decision period setting, you'll see that it's set to 5 by default. This means that a decision request will be sent roughly every 5 physics steps. By default, a physics step occurs every 0.02 seconds. So with this setting, a decision request should be triggered about 10 times per second. Now let's look at the decision step setting. This setting offsets when the decision request happens, even among agents with the same decision period. It helps prevent multiple agents from making decisions in sync, which can sometimes lead to unnatural behavior. The decision step can be set to any value from 0 up to 1 less than the decision period. For our project, we'll leave the decision step at 0, since we only have a single agent. Lastly, we have the Take Actions Between Decisions setting. When enabled, the agent continues its last action while waiting for the next decision, keeping movement smooth. If disabled, the agent will remain idle between decisions. For our turtle agent, we'll leave this enabled. Alright, let's go back to the TurtleAgent script. Go to the Max Steps field and set it to 5,000. Max Steps defines how long an episode can last before it automatically resets. If an agent hasn't reached its goal within this time, the episode ends and training continues. For our project, we've set Max Steps to 5,000, which gives the agent plenty of time to learn, while ensuring it doesn't get stuck indefinitely. Okay, our scene setup is almost complete. Before we start training, I just want to fix a couple of visual issues. First, I'll adjust the main camera position so we get a good view of the environment during training. Feel free to use these camera transform settings. The other issue I've noticed becomes evident when running training or inference, especially if you move the camera close to the turtle. As you can see, it looks like the turtle is hovering in mid-air. This is because the turtle's capsule collider extends way below its body. We can fix this by simply moving the capsule collider upwards until its bottom aligns with the bottom of the turtle. Let's do that now. Select the turtle game object and go to the inspector. Find the capsule collider and adjust its center values. Set X and Z to 0 and set Y to 1.34. The bottom of the collider should now be flush with the bottom of the turtle. Since we have changed the collider's position, we need to change the starting position of the turtle accordingly. We will do this in the TurtleAgent script, so let's open it now. Scroll down to the Spawn Objects method. If you remember, this method is called at the start of each episode, and we can see that it's resetting the turtle's position. Let's adjust the Y-axis component of the start position vector. Set it to 0.15. Save the script and return to the Unity editor. I'm just going to readjust the scene view and take a look at our current setup. It looks like we are ready to kick off our first training run. So let's save the current scene and then switch to the desktop. Be sure to keep the Unity editor open, however. Open an Anaconda PowerShell prompt. We're going to reactivate the Conda environment we set up in part 1 and use it to launch a training session. This will involve typing some Conda commands. I've provided a link to a list of these commands in the description. Okay, let's get on with it. In the PowerShell terminal, type Conda activate ML agents. Our ML agents environment is now activated, and it already has the ML agents Python package configured. To keep everything organized, we want the results of our training, such as the AI model or policy, to be saved inside our Unity project folder. To do this, we need to launch the training session from the root of our TurtleAgent Unity project. So, let's change the directory in the terminal accordingly. Enter this command. From this point on, all commands will be executed from within this folder. Now let's double-check that the ML Agents Python package is working correctly. We can test this by entering the following command. If this help readout appears, then everything is okay. We can go ahead and run a training session. To start our first training session, type the following command. Before I press enter and execute this command, let's quickly go over what the runID parameter does. The runID parameter gives this training session a unique name. This is important because ML Agent stores all training data, like AI models and debug logs, inside a dedicated folder. Specifically, all training results are saved inside the results folder, and within that, a subfolder named after the runID. For example, by setting runID equals turtle1, all data for this training session will be saved inside results/turtle1. This helps us keep multiple training sessions separate so we don't accidentally overwrite previous results. Okay, let's get back to the PowerShell terminal. Go ahead and execute the ML Agents learn command. The ML Agents Python backend should now fire up. Once you see the Unity logo, you'll know that ML Agents is ready to begin training. ML Agents will prompt you to start training by pressing the play button in the Unity editor. So let's go ahead and do that now. Switch back to Unity and press the play button. Unity will connect with the ML Agents Python backend and training will begin. The turtle agent should start to move, admittedly rather erratically at first. You will also notice that the environment resets at intervals. This happens either when the turtle reaches its goal or when max step is exceeded. Whenever this occurs, a new episode begins. I recommend keeping the PowerShell terminal visible alongside the Unity editor, as it will keep you updated on the progress of the training session. Alright, let's stop training for now. In the Unity editor, hit the stop button. Take a look at the PowerShell terminal, and you'll see that it has registered that Unity has disconnected. At this point, You could click play in Unity again, and the current training session would continue. However, if you wait a little longer, the session will eventually time out and fully terminate. If you now want to restart a training session, you have 3 options depending on what you want to do. Option 1 is to restart the training session using the force parameter. This will completely reset the training session for Turtle 1, deleting all previous progress and starting from scratch. Option 2 is to resume the previous training session using the resume parameter. This lets you pick up where the last Turtle 1 session left off, continuing training from the saved model instead of starting over. Option 3 is to start a completely new training session using a different run ID. For example, by setting the run ID to Turtle 2, you'll train a brand new model while keeping the previous results from Turtle 1 intact. Alright, that's about it for this tutorial. In the next video, we'll take a more detailed look at how training works, including ways to train more effectively. I'll also introduce some methods for debugging and assessing our training progress. So if you found this video helpful, don't forget to like and subscribe. Goodbye, and I'll see you in the next one.